analyze the differential amplifier with different configuration, we have to use R parameter instead of H parameter for a number of reasons. Number one, because of the nature of R parameter, AC analysis of differential amplifier with R parameter is simpler, more straightforward and less cumbersome. Unlike with H parameter, there is no need to manipulate R parameter at different operating levels, that is, different emitter current and different collector emitter voltage values, except for RE value. The performance equation obtained are easy to remember since they are not as complex or as lengthy as H parameter equation would be. Above all, the results obtained using R parameter compare favorably with actual result, or we can say that we can compare the actual result with the result obtained using R parameter. First of all, we would like to analyze dual input balanced output differential amplifier. The circuit shown in figure 1.2 in the previous page is a dual input balanced output differential amplifier. Notice that two input signals, that is V in 1 and V in 2, are applied to bases B1 and B2 of the transistors Q1 and Q2. The output V out is measured between the two collectors, that is C1 and C2, which are at same DC potential. Because of the equal DC potential at two collectors with respect to ground, the output is referred as balanced output. We can say that as the equal DC potentials are available at the collector with respect to ground, that's why it is referred as balanced output. First of all, I would like to analyze the DC analysis to determine the operating points, that is ICQ, that is collector current at quiescent point, and the collector emitter voltage at quiescent point. For a differential amplifier, we need to obtain a DC equivalent circuit. The DC equivalent circuit can be obtained simply by reducing the input signals V in 1 and V in 2 to 0. Means we have to replace V in 1 and V in 2 by a voltage source with 0 voltage. The DC equivalent circuit thus obtained is shown in figure 1.3. Note that the internal resistances of the inputs are denoted by R in, because R in 1 and R in 2, they are equal. We are assuming R in 1 and R in 2, they are equal. Since both emitter bias section of the differential amplifier are symmetrical, we need to determine the operating point, collector current ICQ, and collector to emitter voltage VCEQ for only one section. We shall determine ICQ and VCEQ value for a transistor Q1 only. These values can also be used for transistor Q2 also. In this circuit, we have replaced V in 1 by a ground, because we have to put V in 1 is equal to 0 volt and similarly we have to put V in 2 is equal to 0 volt. Now we will apply KVL to the loop. This is the DC equivalent circuit of dual input balanced output in which we have done nothing but only replace V in 1 and V in 2 by 0 voltage, that is grounded. And second change that we have done is we have replaced R in 1 and R in 2 by R in, because both are equal. Now we will find the ICQ and VCEQ only for this transistor Q1, and same may be applied for the transistor Q2. Now we will apply Kirchhoff's voltage law to the base emitter loop of the transistor Q1. Minus R in IB minus base emitter voltage minus RE twice 2I plus VEE is equal to 0. But since IB is equal to IE divided by beta DC, where beta DC is the current amplification factor, since IC is approximately equal to IE. Thus, the emitter current through the transistor Q1 is determined directly from the equation 1.1 and is obtained as IE is equal to VEE minus VBE divided by twice RE plus Rin divided by beta DC, where base emitter voltage is equal to 0.6 for silicon transistor and zero point 0.2 volt for germanium transistor. Generally, R in 1 divided by beta DC is much less than twice Re. Therefore, we can replace this term by a 0 and obtain the equation IE is equal to VEE minus VBE divided by twice RE. From equation 1.3, we see that the value of Re sets up the emitter current in transistor Q1 and Q2 for a given value of VEE. In other words, by selecting a proper value of Re, we can obtain a desired value of emitter current for a known value of VEE. Notice that the emitter current in transistor Q1 and Q2 is independent of collector resistor RC. Now we shall determine the collector to emitter voltage VCE. The voltage at emitter of the transistor Q1 is approximately equal to minus emitter base emitter voltage if we assume that the voltage drop across R in 1 to be negligibly small. We say that R in is approximately equal to 0. That's why the voltage drop across this R in is approximately 0. Known the value of emitter current IE, which is approximately equal to IC, we can obtain the voltage at collector VC. VC is equal to VCC minus RCIC. Thus, the collector to emitter voltage VCE is VC minus VE. Place the value of VC and VE. VC is VCC minus RCIC minus again the value of emitter current is approximately equal to negative of emitter base emitter voltage. So we obtained the collector voltage collector emitter voltage as VCC plus BEB, that is base emitter voltage, minus RCIC. Hence, for both the transistor, we can determine the value ICQ and VCEQ by using the equation 1.2 and 1.4 respectively, because at the operating points I is approximately equal to ICQ and VCE, that is collector emitter voltage, is equal to VCEQ. Remember that the DC analysis equation 1.2 and 1.2 are applicable for all the four differential amplifier configuration as long as we use the same biasing arrangement as discussed. In this case, we are using emitter biasing arrangement. That is, knowing the DC analysis procedure for one configuration, that is dual input balanced output, we do not have to repeat the DC analysis procedure for remaining three configuration, because the equation 1.2 and 1.4, they are applicable to all the configurations of differential amplifier. In the next lecture, we will discuss the AC analysis. Till then, bye bye. Thank you and all.